So thank you very much. It's a great pleasure to be able to talk to you, although of course it would be much nicer to be there in person. I've never been to Moscow, and it's one of the places I'd really like to go one day, and hopefully it will be possible. So I'm going to talk about active matter, and in particular, dense active matter. So let me start by telling you what active matter is, and then just give you the reasons why I think it's fun to do research on this. So active matter is material which takes energy from the surroundings as individual particles and then uses it to do work. And thinking about it a bit, that's essentially biology, because things like cells take energy from their surroundings in the form of ATP and use it to move around and to move molecules around within the cells. Everything alive is essentially active matter, but we tend to think about the small things like cells or molecular motors because we can start to understand what's going on there. So why do we care? Why do we care about looking at active matter? Well, let me show you one of my favorite movies. This is Drosophila, the fruit fly, a fruit fly embryo. And what those little white dots are cells. And this thing is growing up to be a fruit fly. And you can see that there's all sorts of amazing changes of shape and pattern formation going on. And certainly there's some biology there. There's certainly chemical signaling. But on top of that, there's mechanics, there's flows, and there's forces. So somewhere here, physics has a role to play in understanding what's going on in this system. And this is collective active matter. It's a creature which is using food to reorganize itself. The other thing nature is very good at is building tiny things. This is the bacterial flagella motor. It sits here between the body of a bacterium and the tail of a bacterium, and it turns to turn the tail so the bacterium can swim. And this is an artist's impression because no one's quite sure exactly what it looks like, but each of these little blobs is a different protein. So somehow nature is putting together this complicated machinery on a really very tiny length scale, which is then able to turn something like 100 revs per minute to propel this little bacterium. We can't do anything as sophisticated as that. And then the third reason why active materials are fun, particularly for a computational and theoretical physicist, is that this really is non-equilibrium statistical physics. Lots of particles together is statistical physics, but here you're putting in energy, and then the energy is continually pushing the system out of equilibrium. And so you've got a testing ground for the theories of non-equilibrium statistical physics. And what we're seeing here is a layer, a dense layer of microswimmers, a dense layer of E. coli. And what's surprising is that you're seeing something which looks a bit like turbulence, active turbulence. And that's strange because these things are tiny, and so you're meant to be at low Reynolds number, and therefore you're looking at a system which looks as if it's turbulent when you're at low Reynolds number. So this is what I'm going to talk about really, this active turbulence and similar problems in biology. Oh, I just wanted to show you the cells, same thing, the same sort of turbulence in a layer of cells. These are epithelial cells, like the cells that line your stomach or line your lungs. And again, you're seeing turbulent-like behavior. So this is what I'm going to do. I'll start by talking about active turbulence and active topological defects. And this is background material, which is pretty well understood now, although we certainly don't have a theory of what's going on, not a real first principles theory. Then I'll talk about my Hare and Tortoise story, which is an example of active topological defects in biology, and then show you some very recent work, which is computational, on active material in 3 dimensions. Okay, so let me just remind you to start with. Let me remind you about the idea of nematic symmetry, because the theory we need to describe these active systems is a nematic theory, an active nematic theory. A nematic has this symmetry. It has a preferred direction, but up and down are the same. And if you take nematic molecules or nematic colloids, then at low temperatures, they tend to order into a nematic phase like this, which has long-range orientational order. They all pretty much point in the same direction, but not long-range positional order. So it certainly isn't a crystal, and in fact, it's a liquid. And the order parameter we'll be worrying about, which describes this phase, is this Q tensor Q, and you don't have to worry too much about that, just that it tells you about the direction of the molecules and the magnitude of the ordering. This is a nematic in Oxford. This is the nematic at high temperature in the summer, and this is the nematic at low temperature in the winter. Although it's too much like a crystal, really. They ought to be a bit more, their centers ought to be a bit less aligned, I think. Okay, so what we're going to concentrate on most, perhaps, around these nematics is the idea of topological defects. Topological defects are places where the ordering goes wrong, and in particular goes wrong in a way which can't locally be put right. I'm going to stick with 2-dimensional nematics, because that's where most of the experiments are, at least to start with. And in 2-dimensional nematics, the main sorts of defects are this one, which is a +1/2 defect that looks like a comet, and this one, which is a -1/2 defect, and you can recognize that by its very obvious 3-fold symmetry. And in a normal passive nematic, the defects just annihilate in pairs, and you end up with perfect nematic order. So they annihilate just like ± or -1/2 charges. So we know how to write down the equations of motion of a liquid crystal. These are the continuum equations of motion of a nematic. So they're a bit like Navier-Stokes equations, but they're more complicated because the nematic has this structure of long, thin molecules. First of all, there's an equation for Q, the order parameter. This is advectored by the flow field. And then you have a term here where I haven't written out the details, but the physics is that as if the nematic is in a shear flow, because it's a long, thin molecule, it's going to get turned by a shear. And then this term here is a relaxation term. It relaxes to the minimum of the Landau-de Gennes free energy. You see Landau's everywhere, relaxes to the minimum. And so in equilibrium, this thing would form a nice equilibrium nematic if there was no flow. You also need an equation for the velocity. And the way I've got it written looks pretty much like the Navier-Stokes equation. This is the usual convective derivative term, and then the derivative of the stress tensor. Here is hidden some more complicated things. You have the usual viscous stress, but also an extra elastic stress, and that takes account of the fact that when a liquid crystal molecule moves, it pushes the fluid and creates a backflow. So we want to extend these to look at an active nematic. So I think it's probably useful to think of an active nematic as a dense collection of these microswimmers, a dense collection of E. coli, if you like. And the extra thing is that each of them is swimming, and so it's producing a flow field. And the sort of flow field it produces looks like this. Here's a tiny swimmer, it produces a flow field which it pushes outwards from its ends and it pulls inwards from its sides. And that flow field has a nematic symmetry. That's actually because this thing is force-free. So in terms of the multipole expansion, you lose the leading term and you pick up the dipolar term. So these things in the far field have a flow field which has nematic symmetry. And that is the physics behind, although I won't have time to do the maths behind, how you extend the nematic equations of motion to describe an active nematic. There's the passive equations. If we want to make them active, we want our little swimmers to swim around, you have to add just one simple extra term, an extra term in the stress, which is just proportional to the order parameter Q and has some coefficient out the front, which measures the number of swimmers, the strength of the flow field, and is called the activity. Note that this Q comes under a derivative. And that's really important, that it comes under a derivative, because what it says is every time there are gradients in the nematic order, you get stresses, and so you get flows. Gradients in the nematic order induce flow. And actually, you can explain an awful lot of what's going on in these active systems by using this idea that gradients in the magnitude or the direction of the order parameter induce flow. So what does that term do for you? If you start trying to solve these equations, what happens because you've got the extra active term in there? Well, for a start, the nematic state is unstable. If I've got a nice nematic state like this and there's a tiny fluctuation, the tiny fluctuation is going to induce flows, changes in the order parameter, gradients in the order parameter, so you're going to get flows. The flows end up being in this direction, and so they increase the fluctuation, and that's just a picture showing you that the system is unstable to any sort of small fluctuation in the nematic order. So in active nematics, the nematic order is unstable, and you cross over to something else. What do you get instead? And that's where you need the numerics. You need to solve these equations numerically. And we do that using a lattice-Boltzmann algorithm for the velocity equation and a finite difference method for the equation in Q. And if you do that, what you end up with is a flow field which looks like that, where you're seeing lots of vortices and the yellow lines are strong flow. So you get strong flow jets and vortices. And if you look at the vorticity, the red bits are anti-clockwise vorticity and the blue bits are clockwise vorticity. You can see these strong vortices, and typically these are fairly long range on the scale of 5 to 10 of these little swimmers. And I actually can't remember whether this is a numerical or an experimental picture. They really look pretty much the same. So we're doing nematics. We've sort of seen this turbulent-like flow. What about the topological defects? In a passive nematic, we'd have topological defects, and they destroy each other in pairs till they've all gone away. So let's now follow the defects in this active nematic. So the red ones are the +1/2 defects, the comets, and the blue ones are the -1/2 defects with threefold symmetry. So here they are moving around, and I can never find the ones which are doing like I want them to. Okay, so they're destroying each other in pairs there and there and there. But then look here, up here. They're also being created in pairs. And that makes sense because these systems are active. They're always taking energy from their surroundings. energy is being pumped into them. And so there's energy in order to make these pairs of topological defects. So what you end up with is a gas of topological defects. Play that one again. A gas of topological defects, which are continually annihilating in pairs and then again being created in pairs. What's more, the topological defects move, or at least the plus a half ones do. That makes lots of sense because this plus a half one definitely has gradients in the order parameter. Gradients in the order parameter means stresses, means flows. And so this thing here, it's obviously got polar symmetry, and so it's going to move, and it actually moves in this direction. And that's really why it can escape from the minus a halves when it's being created. This one here produces flows as well, but because of the symmetry, they balance. So if we look at the flow fields around those defects, this is the plus a half, and the flow field has these two vortices on either side. This minus a half has a six-fold pattern of vortices around it. And if you could remember that, because we're going to see it again in the next bit of the talk. Just to show you it really works, this is a picture of active turbulence in a system which comprises microtubules, long polymers, driven by molecular motors. And what you see is again a turbulent state. And when you're used to it, there are really clear defects in here. I'll show you when it stops. Okay, so there's that threefold symmetry of a minus a half defect. And here is the shape, the comet-like shape of a plus a half defect. Okay, so that's the conclusion of the first bit of the talk. Active pneumatics really you get active turbulence. Active turbulence is not like inertial turbulence because the energy is input at small length scales, and you end up with these active topological defects, and in particular, the plus a half defects are self-propelled. So what? I mean, that's fun theoretical physics. Do we ever see these things in real systems? So now I'm going to talk about the story of the hare and the tortoise, hoping that this will travel across boundaries between countries. This is work done with some super colleagues who at the time were at Oxford and have now, the young people have moved on to other places. So now I'm talking about another sort of active system. I'm talking about bacteria which don't swim, but which crawl. They have pili, which essentially are little legs, and the little legs push them along a surface. And here you can see them moving. And in the movie, you can, let's see if we can play it. Oh, sorry. That's it, play it again. Again, you can see it looks like active turbulence. And you can see local regions of pneumatic order, certainly not long-range pneumatic order, but certainly local pneumatic order. One of the big questions at the moment with bacteria is what happens with mixtures of different sorts of bacteria. The particular question we wanted to ask here was if you mix together two sorts of bacteria, which move with different speeds, what happens in terms of how quickly they can spread out and colonize their surroundings. And so we made a mixture of two different sorts of bacteria, well, we as my experimental colleagues, the wild type ones, which had a normal number of legs, and genetically modified ones, which had extra legs, and which therefore moved faster. And so on average, these guys moved about twice as fast as those guys. So now let's look at them spreading out. So they're starting here on the right-hand side of the screen. And the ones at the top are the slow bacteria. And these here are the fast bacteria. and let's see how quickly they spread. There we go. So the ones at the top are the slow ones. Let me play that one again. I can do it. The beginning is under pictures of you, so I'm a bit confused when it's at that side of the screen. Here they go. Yes, that's right. Okay, Hare and the Tortoise. The slow ones win in the end. And that's strange. So we've got something to explain there. Let's also look at what happens near the edge of the colony. The fast ones are yellow and the slow ones are blue. At early times, the fast ones are definitely dominating the edge of the colony. But at later times, you get so you can't really see any fast ones anymore, and you get these blue ones instead. So somehow, the slow ones are doing a better job of spreading out. Well, from what I've said, it's pretty much something to do with topological defects. So let's look at the topological defects in this system. Red ones are the +1/2, and the blue ones are the -1/2. And you can certainly identify topological defects because of the local nematic ordering. How would you model these? Well, the very simplest way to do it is just as hard rods with a force acting on each rod and an overlap potential, which we took to be a Yukawa potential. And if you look at topological defects in this system, again, you can see them, and that's fine. And we already saw the topological defects in the continuum model. So you might well be saying, you know, so what? Why is one set of topological defects the same as, and how do I know the same in the experiments and the models? And so we tested the flow field around these defects, the flow field around +1/2 defects down here on this line, and -1/2 defects up there on that line. And you can see that, well, we've seen this before, 2 loops here, 6 loops for the -1/2 defects. This is the rod simulations. You can see the same structures, not quite as clean because of the fluctuations, but it's not bad. And here are the experiments. And there the fluctuations, the noise is even worse because these are hard experiments, but you're seeing the 2 vortices here, and up here 6 vortices around that -1/2 defect. So at least to the extent of the flow fields they're creating, these defects are the same in the experiments and in the simulations. Fine. But I haven't yet explained what that's got to do, if anything, with this problem of the Hare and the Tortoise. So let me show you what happens when you look at these things through a microscope from above. You get blobs. This is looking at the bacteria from above. You get these localized regions. That's twice through with different graphics. And what these localized regions like this are, is it's places where the bacteria are standing up on end. So what happens is that somehow they form clusters which are standing up on end, and that happens more easily with the fast bacteria. And because the fast bacteria get stuck in these islands which are standing up on end, they end up not being able to spread. Let me say that again about what happens. What happens is that 2 +1/2 topological defects come towards each other just by chance, and they tend to rotate around each other. This causes forces, and the forces make the bacteria stand on end, at which point they get stuck. This only works if the bacteria are moving quickly, because if the bacteria are moving quickly, the topological defects move quickly, and then they have enough energy to form colonies which stay there. Otherwise, the standing up colonies fall down again. Let's see that in a simulation. The defects come together, the bacteria are pushed, so they're pointing out of the blackboard or whatever it is. Okay, the slow ones fall back down again. The fast ones form vertical colonies. Same again, different sort of picture. The slow ones don't form these vertical colonies. The fast ones do. And so what happens is that the fast ones get stuck in these vertical colonies, leaving the slow ones much more efficiently to spread out. I've shown you simulations rather than experiments because they're perhaps easier to see first time through. But Ollie did some absolutely beautiful experiments seeing the same thing. Really difficult because you have to get exactly the right place where this is happening. So even though these aren't quite so pretty, they're very, very clever. Here are the defects, they come together, and here's the formation of the vertical colonies. Here's the final state with the yellow bacteria, the fast ones, preferentially in the colonies, and looking for the side, you can see that they're sticking up, and these colonies will grow and grow. The slow blue ones will escape, and they will be able to spread. So it seems that topological defects are relevant, at least in this system, in terms of the right speed for the bacteria to allow them to spread as efficiently as possible. Let me just show you this nice picture. Okay, know what's going to happen. Oh, she's the one that gave us a seminar about the tortoise. Right, so 3 dimensions now. This is new work, this is unpublished work. If we want to claim that biology is like active matter, there are many things in biology which are 3-dimensional. Clumps of cells, tumors are probably the best known ones, things like the brain. And so it would be nice to understand how active matter behaves in 3 dimensions. And there's some beautiful experiments in Zvonimir Dodik's group which are starting to be able to look at this in a synthetic system. So it's a good time to start worrying about 3 dimensions. And in particular, we wanted to ask what a droplet of active matter does. How does it behave? The person who did it is Liam Rusko, who's actually just a first-year graduate student who's been doing an absolutely brilliant job during lockdown and really beavering away and getting this work done. Okay, so in 3D, rather than topological defects, one has lines of disclinations. And looking at the cross-section of the lines of disclinations, they can either look like a -1/2 defect, or they can look like a +1/2 defect, or in the middle, they can have a twist configuration where the director twists in and out of the cross-section. And so what happens is that the drops look like this. Here's a droplet, and these things that I'm drawing here are these disclination lines, and the points here are where they cross the surface. So inside the drop is just an active nematic, and we're solving exactly the same equations as I showed you before. But the extra thing is an extra equation which describes how a phase field phi evolves. And what this does is it tracks the inside and outside of the drop with a diffuse interface inside the drop and its surroundings. And that interface has the normal surface tension, but also a Helfrich bending energy. And then you choose the free energy and you allow it to depend on this variable phi so that you have a nematic state inside the drop and an isotropic state outside the drop. Now it turns out, I should also say, yes, that I'm going to have to distinguish between a positive activity, which corresponds to a flow field which looks like this, which pushes out the end of a swimmer and in from the sides, and a negative activity where the flow fields are reversed. The important physics is something called active anchoring. And this is very much something which happens in active systems. And we were quite surprised how strong it was in 3 dimensions. At the surface of the drop, the order parameter changes. It changes from a finite value inside the drop to a 0 value outside. Changes in order parameter causes stresses, causes flows. So they're going to be surface flows in this drop. And it's the surface flows cause an effective anchoring of the nematic, of the active nematic. And so the active nematic tends to lie in the plane at the surface if the flow is extensile, and if the flows are contractile, it does the opposite, and it tends to lie perpendicular to the surface. And it's this which controls very different behavior of extensile and contractile active pneumatics in 3 dimensions. The extensile ones, what happens is that wherever you have the end of a disclination being a +1/2 defect, +1/2 defects give flows, and the flows cause parts of the drop to be pushed outwards in fingers. So the active flows are pushing out fingers. The disclination lines tend to form across the fingers and keep pushing, and the resultant flow fields keep pushing these bubbles outwards. Perhaps it's easier to see on a movie. You can see you're getting these fingers formed, which push outwards and then collapse back inwards again. That's the extensile systems. The contractile ones automatically like to have perpendicular alignment at the surface because of active anchoring. But the trouble is that wherever a disclination line gets to the surface, you tend to have in-plane director alignment, and so that's bad. And so what happens is that to minimize that, you get two of these places, 2 of these surface defects joining up with each other with a line of in-plane alignment between them. And then because of this, the activity ends up giving you a shape like this, where each of these surface lines, where each of these lines join a surface disclination, are pushed outwards, giving the drop a wrinkled appearance. In a movie, what happens is this. You end up wrinkling. This is just as a result of the activity. Same equations as in 2 dimensions. And then the other thing which can happen is that if you end up with a very small drop, so that the drop is too small to form disclination lines, it wants to have perpendicular anchoring at the surface. And so it's going to have a huge defect in the middle. It's going to look like a hedgehog with a defect in the middle. And that has a very high energy. And so that's not going to happen. What happens instead is that the drop forms a ring of in-plane anchoring around its middle. This can become unstable and move upwards. As it moves upwards, it creates flows, and that pushes the drop to invaginate. It pushes the drop to form a cup shape. So lots of possibilities, lots of possibilities. We don't understand yet if and how that's related to biology, but I'm sure there's lots of future in trying to understand these 3D active systems. So let me finish with an example which shows just how much we have to learn. I showed you the movie which was of cells on a substrate and the show active turbulence, but then suddenly they take off and start moving in a circle. You can see the same thing in the active models, and we're not sure why it happens, at least in the real cells. And then other sets of cells, these are the ones which line the Drosophila egg sac, don't move like that at all. They somehow manage to coordinate their motion and move in the same direction. And so somehow a mixture of mechanics and biology is causing all these amazing different behaviors. I'll stop there. I've put up some of the references for this. Thank you very much for listening. Okay, thank you.